Okay, excellent. So Will's going to talk to us about viscoelastic rising bubbles and the level set method. So yeah, without further ado, away you go, Will.
Cool. Yeah. Hi everyone in the room. I'm Will. I'm second year PhD. I'm based in engineering, but I did my undergraduate and masters in maths, and I'm obviously co-supervised by Tim. So obviously half of my heart is still in maths. But today I'm going to talk to you about viscoelastic rising bubble level set method, which is my sort of broader research area, I suppose. And the way I'm going to break it down is the first part of the talk is going to be purely about multiphase flow and the formulation that I use to model it, which is obviously the level set method. And then the second part of my talk is going to be on viscoelasticity, which is the real sort of application that I'm using the level set methods for. So to start off with like a little bit of motivation, there are some challenges that kind of helps to think about initially when you're simulating rising bubbles or just simulating multiphase flow in general. First of all, there's going to be an interface between the two phases of fluid that you need to track and define, and you could think to do it with nodes and intervals connecting them, but sometimes that may not be good, which I will come on to describe in a second. But there are other things as well. So for example, the diagram here shows that the larger interface on the left should be able to split into two more interfaces on the right if the dynamics of the flow field define that it should. And then these should be the interface. You shouldn't have to have an extra level of complexity in order to kind of define two interfaces instead of one. They should just be part of the same interface in terms of that object. And then also on the interface, there's going to need to be conditions because you need to define how what happens to the velocity as you cross over the interface from one phase to the other. And then also on the top with the green arrows, you need to define what the state of stress is like across the interface, because obviously surface tension is a force that we need to take into account. So these are all kind of things we need to remember and consider when we're building some sort of multi-phase flow simulation. So as an initial example, one type of way that you can do this is purely explicit, and an example of this is the front tracking method. And it kind of comes in two different flavors. You can go for a Lagrangian approach where the interface kind of deforms almost like a boundary condition, and then the mesh maps to that. So this is really useful when you're modeling things like free surfaces. If you have some sort of wave moving over the top of or on a free surface, then it helps to be able to just move your and kind of adapt it like that. And then comparatively, there's the Eulerian approach where you have the interface defined a level above the rest of the mesh on the velocity field, and you kind of advect the nodes on the interface like that with the rest of the velocity. But there are some issues with this. Some are specific to my research area, some are more general. But one of the main ones is that the topology can change, or if the topology changes quite drastically. So if our interface splits and deforms and makes more interfaces that aren't connected to the original one, then you kind of have to add another level of complexity specifically in your computer code in order to account for this. Another issue also is obviously the material parameters in the fluid will obviously be discontinuous across the interface. So that's another level of complexity, defining the smoothing algorithm across the interface for these parameters. And then you'll obviously need some type of remeshing. It's quite clear that you need remeshing for the Lagrangian approach, and then for the Eulerian approach, if the kind of front of the bubble kind of envelops quite a lot, then the nodes are going to be less spaced out as they need to be. So you need to put them in the right place in order to remain at the same degree of accuracy. So these are kind of some of the issues with an explicit representation. I'm now going to talk to you about an implicit representation, which is what the level set is, or the level set method is, and why I like to use it. So essentially all the level set method is that instead of actually rigidly defining the interface, we define a greater surface and then advect that surface in the velocity field and take only a part of that surface as your actual interface. So the way it works is that we take our level set function phi and make it just a signed distance function. So you can see in figure 3 here, we have our initial interface defined as this circle. And then inside the circle or inside the bubble, you just take the positive difference from the interface, and then outside you take the negative distance. And that way we can take the zero contour of this, or the zero level state, as our interface. So it's defined implicitly as the contour of some greater surface that we define. And then we can advect it in the velocity field using an advection equation. And there are some certain inherent properties to this function as well. So in the second bullet point on the left-hand side, we have this iconal property where the absolute value of the gradient is 1. So we have just linear increase with respect to spatial dimension sort of everywhere. And this will be really crucial for something I'm going to come on to in a second. But how does this work in practice? So obviously I've described that, we have it defined as this greater surface, but it's not immediately apparent as to why this is so good. But this image here does quite a good job of explaining that. As our contour gets deformed, its topology can change quite massively. And you can see here that the difference between the far left and the far right is that the topology has changed so much that the contour is split into 2 separate contours, which is one of the things that we were talking about earlier. But the corresponding level set function for these contours is exactly the same topologically anyway. It's continuous, it's smooth everywhere, there's no cuts or holes or anything, it's remained nice and smooth. So in a way, hello? Oh, I think I heard an echo, sorry. So the level set function will stay exactly the same topologically as you advect it in the velocity fields, but the contour can change and get it completely messed up as you want it to. So here is kind of all of the formulas and equations that I use in order to use the level set method to model multiphase flows. The equation at the top is just the Navier-Stokes equations adapted for a two-phase flow. So you have phase-dependent material parameters, and then we're introducing surface tension now as a body forcing term. The material parameters are now smooth between the two phases using a continuous Heaviside function. And then the second and third bullet points there are the interface boundary conditions that I mentioned on the first slide. So we have the jump of the traction vector across the interface is equal to a surface tension term, and it's negative just purely because of the direction of my normal vector, whether it's pointing out or into the fluid, or out or into the gaseous fluid. And then we also have a velocity jump. Or we don't have a velocity jump, whichever way you look at it. All that says is that as you cross the interface, the velocity should be same. So you have a continuous transition between velocities, which I suppose would make sense. And then a key sort of equation that we also need to solve in tandem with these is a reinitialization equation. So as I mentioned before, the sign distance function has a really crucial property. It has that iconal property that the absolute value of the gradient is equal to 1. As the level set function gets advected through space, due to the hyperbolic nature of the advection equation, it starts to lose this property. It starts to increase, and it starts to get more and more unstable. But we want to retain that property because that is smooth and continuous and nice and kind of prevents it happening more and more in the future. So in order to do that, we solve this reinitialization equation sort of in tandem with the advection equation to recapture the lost properties of the iconal property and make the level set function that we are advecting more like a sign distance function. So this is really, really important too. I'm going to talk a little bit about mass conservation as well. So in certain multi-phase simulations, specifically ones where there's potentially a high Reynolds number, or you have large stress gradients, which are quite important for my research, so you need to guarantee conservation of mass, because if you don't, your bubble will shed mass quite rapidly, just due to the nature of the previous level set method that I was talking about. So we create a conservative level set method just by changing our reinitialization equation and also changing what we use for level set function. Instead of using a sign distance function, we're going to just use a continuous Heaviside function, like the one there in figure 5. And then in combination with that, in the conservative form of our advection and reinitialization equations, we can ensure mass conservation. So the majority of simulations that I do now are based on the conservative level set method, just because it is quite crucial when modeling viscoelastic flow, which I will get onto in a second. But I just wanted to take a second to show you some benchmark data from some quite popular publications. The ones that are quite important here are obviously the TP2D, free life, and populations, which are kind of like the standard benchmarks in the field, and then mine are in the current results table. And they're chosen because they all show different types of cusp shapes. Some show quite thin cusps, some show slightly thicker ones but broken up, and some show ones that have completely broken up. So there's a wide variety in different types of cusp shapes depending on what type of code you're using, how sharp your interface is, how much you're reinitializing. It varies quite a lot between different types of code. I think what I like about my results is that it kind of combines some of the key information from the free life and the Mu and ND simulations. So I have quite thin cusps, but I also have quite large trailing edges as well, so it kind of captures both types of information. So that kind of ends the viscoelasticity section of the talk. I'm going to now talk a little bit more about, that ends the multiphase part of the talk. I'm now going to talk a little bit about viscoelasticity and some of the phenomena that's associated with it. So when you're going from a Newtonian fluid to a viscoelastic fluids, you now have to include forces due to elasticity when the fluid is undergoing deformation. So you include another term in the Cauchy stress tensor, and then this term is then evolved in time with a constitutive law. There's lots of different types of constitutive laws that you can choose due to just the wide variety of nature that viscoelastic fluids kind of show in experiments. The one here is just an Alderode B constitutive model that links the upper convective time derivative, which is just the rate of change of stress following a fluid particle equal to the deformation gradient. But obviously it includes the possibility of the fluid rotating and stretching and things like that as well. So I'm not going to go too much into detail in like the equations in depth, but essentially whenever you include viscoelasticity, because this is a differential equation on tensors, it becomes a much harder problem to discretize and solve. You have many more degrees of freedom, and also it doesn't help the equations are hyperbolic in nature, which means that you need some sort of external stabilization methods in order to make your code not crash, basically. But on the right hand side here, I've got a few examples of some two-phase viscoelastic flows, some quite popular ones. So the one on the top is the rod climbing experiment, where a rod is placed in a viscoelastic fluid, it's rotated, and the fluid actually sticks to it, it climbs up it. And then the second one down is the die swell effect, where viscoelastic fluid is pushed out of a die, and it mimics the container that it was in for the immediate sort of exit from the die itself. It seems like the transition from the no slip running condition inside and then a free slip running condition on the outside. So I'm going to now talk a little bit about some of the phenomena associated with viscoelastic rising bubbles. And the first one, which is incredibly common and seen quite a lot, is a trailing cusp shape. So depending on the simulation parameters, there is a critical volume that's associated with any type of viscoelastic rising bubble. And if your volume is larger than this critical volume, then it will change the characteristics of how the bubble rises quite significantly. So as you can see here in figure 8 on the right hand side, our bubble is supercritical. So we've formed a trailing cusp, quite an obvious one, and it's really starting to form this teardrop shape. And as this bubble will rise, it will get more and more pronounced, and it will pull out and form quite a thin filament on the right, on the bottom. And on the left hand side, we've got a subcritical viscoelastic rising bubble, which hasn't got a very prominent cusp at all. It still probably will form one, given the simulation time, but these two are taken at the same time, and you can see the massive difference in the one on the right. The reason this forms is because when you increase the volume, you increase the buoyancy force that's felt on the bubble. This in turn increases the elastic forces inside the fluid because they're dependent on the rate of strain, which then leads to an increase in extension rate. So you can see the bubbles kind of being pulled out. And the reason for the shape of the cusp being the way that it is due to the next phenomenon that I'm going to talk about. So one of the other quite common phenomena to model is the negative leak. So you can see here that in a region directly behind the bubble, the velocity is going to invert and pull back down, but you've still got sort of conal parts of the velocity field pushing upwards. This creates vortices and it impacts the negative wake and pulls right down. And that is what causes the particular shape of the cusp, but there's also other reasons why it can form. For example, experimentally, it was shown that no negative wake has been found in boga fluids. Now, boga fluids are constant viscosity elastic fluids. So this suggests that there's some interplay between the shear thinning nature of viscoelastic fluids, but then also the elasticity itself. So you need both, you can't just have one or the other. And then also a negative wake wasn't found experimentally in falling sphere simulations, so just dropping a sphere in a viscoelastic fluid, which suggests that it doesn't really have anything to do with interface deformation, which is quite an interesting result. Now, the last phenomenon that I'm going to talk about is kind of the most interesting one. Oh, before that, spoilers. Here are some experimental simulations or some simulations that I did of the negative wake. And you can see here in the second and third images for the time profiles 0.131 and 0.181. You can see the start of the negative wake in the first one, and then it kind of almost halfway through in the second one, you can see it's really starting to increase and pull down. You can see the distance for velocity or vorticity fields as well. And the amount of deformation that the interface goes through is quite extreme. It starts as just a similar sort of teardrop that I showed you in the first one, really starting to get pulled down and down and down. And then in the right, you can see that the negative wake has ended, the velocity is rebounded back up because the elastic energies run out in the fluid, and the bubble is going to start rising again. So, like I said, the last phenomenon that I'm going to talk about is the velocity jump discontinuity, which is really interesting because it's kind of almost a natural example of a continuity in nature. So when you plot the rise velocity of the rising bubble against the volume, you can see that if you increase the polymeric concentration, you get actually quite a sharp, abrupt increase in the rise velocity, akin to a discontinuity. And this can be up to 10 times that of like even a bubble that's slightly subcritical than that value. So it's a really interesting mechanism. There's loads and loads of different possibilities as to how it's formed. One interesting thing that it has in common with the trailing cusp and the negative wake is that the formation of a trailing cusp and the negative wake is a necessary but not sufficient condition for jump discontinuity to occur. You can have these two, so you can have a trailing cusp and you can have a negative wake, but that doesn't necessarily suggest that you're going to get a velocity jump. It's a much more specific mechanism that happens. But we do know some things. We do know the fact that it is tighter bubble volume, similar to the two previous phenomena. There is some interplay with viscoelasticity due to the fact that obviously a boga fluid doesn't experience a negative wake and you need a negative wake. Also, viscotropy is interesting. So there was, as I said with the boga fluids, because they weren't shown experimentally with constant viscosity fluids, it was suggested that you could have a shear dependent viscosity or time dependent shear viscosity. So viscotropy could be a thing. And also the presence of no slip boundary conditions is quite important as well. And it's something I'm working on at the moment in trying to build an axisymmetric 3D simulation to kind of guarantee no slip boundary conditions, but even in a 2D simulation. And we think that the fact that there's no slip boundary conditions on the boundaries kind of forces the cusp in and makes it more formed. And then when you have a sharper cusp, you have more drag forces, or less drag forces, sorry, and then the jump discontinuity becomes more prevalent. So that's kind of the main sort of part of my research, essentially. Yeah, just to conclude, I do have an animation here. Hopefully, it'll work. I think that's rising. Yeah. So that is essentially the crux of my PhD, is kind of modeling these different phenomena to quite a high degree of accuracy. And then also explaining why they happen and their interplay between one another, and how we can control it. But yeah, thank you for listening to my presentation. Hopefully that all made sense. You can see this lovely Newtonian bubble rising here, similar to the simulation I showed you before. Are there any questions? Thank you very much.
Yeah. Yeah, thanks a lot, Will, for a really engaging talk. So yeah, any local questions first? Or anyone online want to speak up or go through the chat? So yeah, I was interested in this next task that you set yourself, Will, about doing like fully axisymmetric things. So at the moment, can you explain a bit more about what you're thinking is not fully resolved in terms of boundary conditions? I didn't quite understand that.
Yeah, so I'm trying to build an axisymmetric simulation. So basically, I don't have to do 3D simulations because 3D simulations are incredibly expensive to perform on computers. So I'm trying to just build an axisymmetric or build a 2D simulation that represents a 3D simulation in a cylinder. And then what I can do with this is then impose no slip boundary conditions on the whole boundary. So similar to here, I can impose no slip on the left and the right in 2D, but then actually obviously it equates to a 3D simulation. And then I'm thinking that will help me in modeling the jump discontinuity to a high degree of accuracy. But that is obviously still a work in progress.
Yeah, no, that's really interesting. So there is like a verified kind of like non-locality of the walls playing a role in the flow. So like you'd be expecting to see different phenomena with different separation distances to the walls, or is it like other length scales are important, or is it just about the kind of relative size of the bubble to the channel?
Yeah, it's a combination of both, and a lot of it really isn't still understood. There's still a lot of analysis that needs to be done on kind of how much of an effect the boundary conditions have compared to sort of the internal properties of the fluid. But it does seem like the simulation setup, so like you mentioned with the bubble volume, that plays a really important role too.
Yeah, that'd be interesting to see. And final one, if there isn't anyone else, yeah, just so have you coded this yourself, or are you implementing your level set method in an existing fluids code?
Yeah, so I kind of left out a lot of the
Oh, yeah.
visualization because it's not particularly interesting. I wanted to focus on the big picture stuff. But yeah, I've done everything using the finite element method. I use a finite element library called Phoenix, which helps me kind of discretize everything. But yeah, build all my weak forms for my equations, do all my stability criteria, all the time dependence. Yeah, all myself.
Oh, that's very nice. Yeah, I was looking into using Phoenix. It seems very flexible and powerful. So
Yeah, it's
yeah,
really
maybe I'll tap your experience on that at some point. Yeah, I think Tim's got his hand up as well.
Yeah, well, thanks for the talk. Just a quick question about comparison with experiments and then using data from the experiments to put into your model. What progress are you making on that?
Yeah, so one of the good things about being in this, there is like a wealth of experimental results. Normally viscoelastic fluids are incredibly hard to model, and like I said, because the systems are so big, not a lot of time has been put into numerically modeling these, but experimentally it's not too bad. So there is a massive amount of experimental results out there. If I go back to one of my slides, I didn't talk about this, but in figure 9, you can see that there's some quite exotic trading cusps that have been modeled there. So what I'm thinking is take the relative length scales in these pictures, kind of map out a contour, and then compare that experimental contour to my contours in the results that I've been showing you here. So that is another plan that I'm going to try and do. So hopefully try and get a degree of accuracy exactly with experimental results.
Yeah, so if we don't have anyone else, I don't think anyone else has got a hand up or anyone in the chat. So yeah, let's thank Will and Tim again for doing their talk. So yeah, I'll close the channel now, and we'll see everyone next week. I think next week's a fully online one. So yeah, nice to see everyone. Thanks for coming, and see you all next week.
Thank you very much.
Bye.
Bye for now.